Today we're going to talk about gases. And I see that slid over again. Why should I not be surprised? Okay, so let me share the slides for gases. And there we go. Make a slideshow out of it. As soon as it wakes up, there we go. There. What you may notice is this set of slides doesn't follow the same pattern as the other slides because the slides that are provided by the publisher just don't quite satisfy. And fortunately, I had access to a set of slides from my predecessor, Dr. John Dynack, who was very generous with his materials, and I just took what he gave me and modified and modified the slides so that they would suit my needs. But we're going to talk about gases today. So gases are, we say, semi-independent particles. As a general rule, the particles in a gas don't interact very much. In other words, they don't repel, they don't attract. And in fact, an ideal gas is considered one in which the particles behave as if nobody else is in the room. If they happen to bump into somebody, it's just like two billiard balls smacking together. So we know the particles are moving very fast. That's been confirmed experimentally. And the gas may be composed of either atoms or molecules. So, example, if it's composed of purely atoms of one element, it might be something like helium. Okay, just a single atom constitutes the particles in the gas. Or it could be a molecule, two hydrogen atoms bound together. That's just an example. But it's a good example because it has historical significance. Helium was recognized as a strategic element prior to World War I, and the United States had absolute control of the world supply of helium because it was obtained from our natural gas wells as a byproduct of purification. And we were stockpiling helium because in those days, one of the uses of helium was in balloons and dirigibles. And that came to be a valuable commodity, especially since the Germans were developing huge airships that could carry large bomb loads over cities like London. So a worldwide embargo on helium was imposed on the Germans to try to keep them from producing these war weapons. Well, that wasn't the only gas that could be used to lift a dirigible, which they called zeppelins. But hydrogen would do it also. In fact, hydrogen is more efficient. There's just one problem. Hydrogen is flammable. So they were taking a huge risk, and they took precautions for using hydrogen in their balloons. But sooner or later, you're going to have a gas leak, and it's going to find a spark. And it happened actually more than once. The Hindenburg accident was really just the nail in the coffin. the final nail. There have been several accidents before then using hydrogen as a lifting gas. But when the Hindenburg crashed, burned, that was the end of the Zeppelin travel. Okay, so these gases can either be atoms or molecules. And one thing that I've stressed, well, maybe I've stressed it in the past, I hope so, is that gases are completely miscible in one another. Miscible is an archaic word that just means they mix uniformly with one another. So when you get two gases mixing together, they form a perfect homogeneous mixture every time. Gases do have mass, right? That was confirmed very early on. All you had to do was create not a cylinder, but a sphere of sufficient strength, and the technology was available early in the 17th century, middle 17th century, where gases could be removed completely from a sphere. You could weigh it before, you could weigh it after, and find out that the mass of the sphere decreased when you pumped all the gas out of it. And you could put various gases back into it and find that they had different masses. So they knew that gases had mass. So it wasn't just that the particles were insignificant toward one another, because they did have mass. And since they have mass, and we know that they're moving very fast, they have kinetic energy. Because kinetic energy is defined by both the mass of a particle or a mass of a substance and how fast is it moving. If the object weighs a kilogram and it's moving, it's moving at 1 meter per second, then you would square that meter per second and multiply it times the mass of 1 kilogram, take a half of it, and that's your kinetic energy. And kinetic energy is in units of joules. So you could say 1/2 and then 1 kilogram, and then 1 meter per second squared. That wouldn't be a joule, that would be a half of a joule, right? Because you would take half of that. But any object that's moving has kinetic energy. And each gas particle has a certain amount of kinetic energy, energy of motion. Now, the problem is that we can't track every particle in a gas. I mean, even in a rarefied gas and under very low pressure, you still have billions of molecules or atoms in that gas. So we have to, for convenience, and because our technology is insufficient and computing power is insufficient to track every particle, we have to consider their motion random. Right? And for all intents and purposes, that's not a stretch. So what we're going to look at today, hopefully finish before the day's out, is how do you understand what a gas is and how it behaves? Well, of course, the first thing that was developed concerning gases is typical of the sciences. Certain laws were formulated to describe the behavior of gases. And we're going to talk about a few of those today. So how individual gases behave and how gases interact when they are mixed together. Then there's this thing called the ideal gas. How does an ideal gas behave? And these laws are formulated in such a way as to express the nature of an ideal gas. No. So, and under normal conditions, fortunately for the early scientists that were investigating gases, gases under room temperature conditions and 1 atmosphere pressure behave ideally. And we'll talk about that again later. So we're also going to look at how these equations that are part of the laws to be discussed can be rearranged, can be manipulated to solve problems. Okay, why should we be interested in gases? Well, the most important gas to us is probably oxygen, which is part of the Earth's atmosphere. And it's absolutely necessary for heterotrophs, as they say. We're heterotrophs, that is, we have to eat other living things or once living things to survive. Autotrophs are like plants, green plants are examples. But they need a different type of gas, right? Most of those, and the plants that cover the earth, for the most part, need carbon dioxide. That is their food, their gas for existence. So when the Environmental Protection Agency proposes labeling carbon dioxide as a pollutant, they are completely wacko, in my opinion. Because carbon dioxide is not a pollutant. Carbon dioxide is food for plants. Now, many atmospheric pollutants exist and are man-made. I won't argue with that. Such as fluorocarbons, fluorocarbons, freons. They constitute a substantial and significant atmospheric pollutant that has an effect on the Earth's ozone layer. Now, whether or not these various pollutants have an effect on global warming is an open question. And whenever you hear somebody say global warming is an existential threat and settled science, you can tell them they're lying. There's no such thing as settled science. Science, by its very nature, is malleable. It changes. Global warming may be happening and it may not be happening. What we do know is that the global climate does change over time. And that's in the geologic record. There's ample evidence for changes, massive changes that occurred over the history of the Earth. The real question is whether man had anything to do with it. And many of these changes, in fact, most of the changes that have occurred in the atmosphere and with the climatic conditions of the Earth occurred before man came on the scene and had a significant impact on the environment. So they still don't answer that question. They just shout you down usually. That is the proponents of this global warming hysteria. Okay. So the question occurred to me, if you look at the history of chemistry and the history of sciences in general, you see that the age of modern science, when man was emerging from the Middle Ages, these investigations tended to focus on gases first. And I'm just wondering why that is. And the only conclusion I can come to is that science generally investigates problems that are solvable. What I mean by that is, if you don't have the technology or the knowledge base to investigate a natural phenomenon, then you tend to look for something that you can investigate. And by the middle of the 17th century, about the only thing that was open for investigation in a scientific way, and there's ways you could quantify it, and ways you could repeat experiments, what we now consider as modern science, were limited to the investigation of gases. And that had everything to do with technology. What instrumentation was available for investigation, and gases were a prime candidate. So scientists investigated gases first, and that was fortunate, actually, because of some of those descriptors that we've given earlier about gases. Because gases tend to act as if they are composed of independent particles. In other words, there are no interactions, very small interactions between the gas particles that might, so to speak, muddy the waters. So it'd be more difficult to tease out these laws and various generalities that you come to regarding matter. So gases lent themselves perfectly to this type of investigation. And then once you learn things about matter by the investigation of gases, you can progress as the technology became available toward investigation of liquids and solids, where the interaction of particles was much more significant. All right. So one of those technologies that became available in the middle of the 17th century is called the barometer. Baro meaning pressure, and meter, of course, meaning measure. So pressure was measured using a barometer. Well, by definition, pressure is a force that's applied over a unit area. So pressure, by definition, is this force applied per unit area. So if you know the area and you know how much force is being applied to it, you can calculate a pressure. But notice that many, if not all, well, not all, but many of these measurements where you have a numerator and a denominator, you're actually describing an intensity factor. And I think I've mentioned that before, intensity versus capacity. Capacity factors are those that change with the amount of matter or the amount of something that's being measured. Intensity factors don't change with the amount. So you could have a pressure measured for that area, or you could have a pressure measured just for that little area. And if the two numbers are the same, it doesn't matter the size. The pressure is a ratio. Right? So this intensity factor is distributed evenly over the area investigated. For instance, at sea level, if I'm standing on the beach at sea level, then my body will experience approximately 14.7 pounds applied force to every square inch of my body. But then that begs the question, why don't I feel it, right? Because there's an equal pressure from the inside pushing out. It's only when the pressure is differential, different pressure inside and outside, that you start to experience or feel it, or in some cases, experience tissue damage. Okay, so pressure is force per unit area. But the first device that was able to quantify this pressure did not give units in these terms. Like, what's the standard for the standard SI unit for force is the Newton, named after Isaac Newton. And the standard for area is a square meter. So Newton per square meter is a standard unit of force per unit area or pressure. But the first expression and measurement of pressure was in terms of the height of a column of mercury supported by whatever pressure was available. And this was developed and perfected by Torricelli, Evangelista Torricelli, who's of course an Italian. And he invented this device in middle 17th century. And basically what it did was he just took a big pool, a container of mercury, and a tube of uniform diameter, which at that time artisans were very good at making these tubes of uniform diameter, and he just closed off one end of it. Then he filled up the tube with mercury and put his thumb over it. And then he turned the tube upside down and submerged his hand in the mercury. And when he did that and turned it loose, he would have expected initially for that amount of mercury to stay in the tube. But in fact, what happened was it dropped. And it kept dropping till it finally stopped. And that difference between the height from the surface of the mercury outside the tube to that inside the tube was a measure of pressure. He correctly surmised that this column of mercury was being supported by air pressure on the surface of the mercury outside. Okay? Now, what's up here in this space, right? Nothing. That was actually the first instance of a vacuum. Nothing is up there. Yeah, you could argue that mercury being liquid will volatilize a certain amount into that space, but not very much. So it's a partial vacuum with some mercury up here. Okay, so a measure of air pressure then was the height of that column of mercury. And he noticed also that it didn't matter what size the tube was. It could be a narrow tube, it could be a wide tube. The height was still the same. So he correctly surmised also that the height was the important factor. And that the air pressure, the force of air bearing down on that surface, and the size of the pool didn't matter either. So that column of mercury was being supported by air. And he noticed also that if he put his barometer in the back of an ox cart and went up a mountain, the level of the mercury dropped. Okay, so that means there was less pressure in the atmosphere that was holding up the column, so the column shrank. And if he went down the mountain toward the sea, then he found that the column of mercury rose, the height rose. And that was indicative of the fact that there was more air above in the atmosphere, bearing down on that pool of mercury, which supported the column. Okay, it didn't take him long to realize that if you let that barometer sit on the desktop and watched it over a period of time, you would notice that when the weather started to get bad, storms were rolling through, the level of mercury dropped. And when the storms passed and the weather cleared, the level of mercury rose again. So there we have low pressure, high pressure being associated with storms or good weather. And that was noticed very early on. Okay. So, on average, and now taken as equivalent to 1 atmosphere of pressure, is a height of a column that is 760 millimeters tall. So this 760 millimeters is what we would consider normal 1 atmosphere pressure, say at sea level. So there you have a conversion, right? You have 1 atmosphere equals 760 millimeters of mercury. Okay, remember, if you have an equivalence, you have the potential for a conversion factor. So if we have something measured in millimeters, we can use this factor to convert it to atmospheres. Okay, so if we have measured on a given day at the Raleigh County Airport, I think it's got a different name now though, doesn't it? Anyway, it's FAA designation is BKW. So suppose we measure the pressure at 694 millimeters of mercury, right? At this altitude, 2,500 feet, that's not unusual, right? Because we're a lot higher. We're half a mile high. So what's the pressure in atmospheres? Well, you've got this millimeters of mercury, and there's your conversion factor. 1 atmosphere equals 760 millimeters, right? But we need millimeters in the bottom, so we can cancel millimeters and leave us with atmospheres. And that translates into 0.9 atmospheres of pressure at the Raleigh County Airport on that particular day. If you go up to Winter Place, right, you've increased your altitude another 1,000 feet. So you're going to find that the pressure has dropped. And now when you convert it to atmospheres, you find that it's dropped below 0.9. It's now 0.88 atmospheres. All right. So suppose you're, let's see, where would that be in this? This could be Death Valley, right, California. You're below sea level, right? So you could measure a pressure that's 1.032 atmospheres, convert that into millimeters of mercury, right? And it turns out that it's 784. Instead of 760, it's higher, right? So we're using dimensional analysis to make conversions between one measurement unit to another. Okay, I mentioned earlier the standard for pressure was 1 Newton force per 1 square meter area, right? These are derived units, right? The standard unit would be meters, and then you derive area from square meters. The Newton is another derived unit. It's based on Newton's first law of motion. Force equals mass times acceleration. If you get a mass of 1 kilogram, and it is accelerating at 1 meter per second, that's acceleration, meter per second squared. Then the the units then would be something like this: kilogram meters per second squared. And that force is equal to 1 Newton. Okay? So we could go backwards and forwards, right? Whatever units we need, as long as we know that conversion and how it was derived, then this derived unit of Pascal, being the standard SI unit of pressure, which is in fact a derived unit, allows us to make conversions backwards and forwards with different other units. Whereas it's a little more difficult with something like millimeters of mercury or atmospheres to make that conversion, right? Because we may not understand what the relationship is, right? So that has to be measured. Other expressions, right? 1 atmosphere is also equal to 29.92 inches of mercury, right? That's fairly easy to do because we know the conversion between millimeters and inches, right? 25.4 millimeters equals 1 inch, right? So you just divide that into 760 and you get inches of mercury. This factor is important when we do our lab for Boyle's law, because the barometer in the laboratory at Raleigh campus gives us values of pressure in terms of inches of mercury. And we're going to find out in just a few minutes that inches of mercury is not a useful unit of measure for doing calculations with these gas laws. We prefer atmospheres. So you need to know that conversion. 1 atmosphere equals that many inches of mercury, and you can make the conversion. PSI, right? So with Boyle's law, we'll also pressurize the vessel for investigating Boyle's law with an air pump. And we'll measure the pressure on the trapped gas in terms of pounds per square inch, because we use tire gauges, right? So it's going to give us those values in PSI, pounds per square inch. Well, those have to be converted to atmospheres too, right? Because you can't add or subtract or multiply or divide units that are various. They have to be the same unit, especially if you're going to add or subtract them. So we have to learn how to convert PSI to atmospheres also. Now, there are other units that are characteristic and often used in other investigations, and the bar is one of them. The bar is equal to this many pascals, right? So it's a pretty large unit if it takes 100,000 pascals to make 1 bar. And if you are interested in weather, you'll find that weather reports generally report pressure in millibars, thousandth of a bar. And they may say, this hurricane has the lowest measured pressure in modern history at so many millibars. But they're all interconvertible, as long as you understand what the equivalence is, right? So 1,013 millibars should be equal to, it doesn't say, is equal to, oh yes, that's equal to 1 atmosphere right here, okay? So these are just examples of converting from one pressure unit to the other. Right? So we're going to take this many PSI and convert to atmospheres. And then we're going to convert to inches of mercury. And that's what inches of mercury would be for that many PSI. say we had millimeters of mercury. We want to convert to millibars. You just need to know what are the equivalences, right? So we can convert to atmosphere, and then atmospheres we can convert to millibars, right, with those units. So here's another chained conversion. You don't have one that will take you directly from one to the other. Well, actually, in fact, you really do. If you recognize the fact that 1,013 millibars is equal to 1 atmosphere, and 760 millimeters is 1 atmosphere, then 1,013 millibars is equal to 760 millimeters. So you could just put that one over the top of this one, and you have one factor. Okay. So if we actually wanted to convert 1 atmosphere pressure to some measure of, let's see, calculate the atmospheric pressure in pascals. Okay. So if the Pascal unit is based upon this 1 Newton per meter square, then it takes some work, but we can do that because we know the height of mercury, we know the diameter of the tube, right? In that case, we know the column, the volume of mercury, right? Height times area, right? If we know the diameter, we can calculate the area, and the area times the height gives you the volume. And then if we know the density of mercury here, and that can give us the mass. What's the mass of that column of mercury? And then the form of this F equals ma that is applicable to what is the pressure in pascals, we need to know the force, right? So the force then would be mass times the acceleration of gravity, which is that little g. So that's the acceleration of gravity that's applied to that equation, right? So we can go through these various steps. We can find out, how many kilograms is the mass of the mercury in that column, and then we can convert that to force per unit area. That's all this is doing, right? And this is just illustration of how to calculate the how many pascals is equivalent to 1 atmosphere. So that's where we got the derived unit. The kilopascals is equal to 1 atmosphere. Okay. I got my animation screwed up here. But what I'm trying to do is introduce the topic of discussion for Boyle's law. That's the first law that was developed for gases. Okay, Boyle's law. All right, who was Robert Boyle? Well, he was an Englishman. And he was very meticulous. He got the idea that science should be quantitative. And he got that idea from other scientists that were dabbling in it. But he was even more meticulous than they were. Lavoisier in France was quite he was a contemporary. But they were interested in quantitative, the measurements that could be applied to scientific investigation. And Robert Boyle is often given credit for being the first quantitative scientist. He published this work in 1662. In those days, it was probably published in Latin, because if you wanted to communicate with anybody in Europe with its various languages, the best way to do it was to publish it in a common tongue, and Latin was it. It was learned and understood by all educated people. Well, what Boyle realized from his data was that there was a relationship between the pressure and the volume of a confined gas, right? And this data set illustrates that. This isn't actually his design. This is later information. Boyle's design of his device was more like a J tube. Torricelli had that long tube that was closed at one end. Boyle just got his glass blower to take that closed tube and bend it into a J shape. So it would be closed here. And open on that end. So there's your technology, right? That's what they had to deal with. This is as far as technology would take them in those days. Glass tubes, okay? So Boyle recognized that now that glass tube is filled with air, a gas, and that was as good as any in those days. So what he did was he added mercury to it. By the way, I don't think they recognized how toxic mercury was, but they certainly knew that it was different than water, but water was more common, right? Mercury, you could acquire mercury, of course, but water was much easier to get a hold of. Why didn't they use water? Why didn't Torricelli use water in his barometer? Or why didn't Boyle use water in his experiments? Well, the key word there is density. If Torricelli had used water in his barometer, his tube would have been 30 feet long, actually more than 30 feet, in order to accomplish the same thing. But with the difference in density, where mercury is over 13 times as dense as water, he could use a shorter tube because the mass of mercury for that height would be higher, and therefore pressing down on that pool of mercury with much greater force. And he may have just discovered it by accident. But Robert Boyle carried on with using mercury, and mercury was the ideal choice because it had two things going for it. One, it was very dense, and two, it was a liquid at room temperature. They couldn't use a solid to do these experiments, and all the other liquids weren't much better than water for density's purpose. Mercury was the perfect answer to this problem. So when he added mercury here, it started developing a pool on the bottom. So you get mercury down here like that. Right? Get a little mercury there. Well, that's not good enough because there's still air all the way through. So he added a little more. Eventually, his pool of mercury touched the inside of that curve. At that point, the gas in the end of that J tube is trapped. So any more mercury he added was going to be applying pressure against the gas that's trapped in there. So he kept adding mercury. Actually, it has a convex curve to it. Like that. And he found that as he added more mercury, the level here never came up to that height. It was always down below somewhere. So he measured and he reasoned that the force being applied against the mercury was equivalent to the height, the difference of the height between that mercury and this mercury. Right? So he used that height measurement as an indicator of pressure against the gas that's trapped in there. And as he got higher and higher and higher, he found that the pressure here, which is approximating the pressure on that gas, could be related to the volume that was in the left in here. So he noticed that the height here is proportional to, actually, the proper symbol here is this one. Kind of a half of an infinity means proportional to. So the height's proportional to pressure here, and over here, the height is proportional to volume. Okay, he could actually calculate the volume in here because the uniform diameter of the tube gave him an area, and then times the height would give volume. So he compared those two values. He noticed that as the pressure increased, the volume decreased. They're inversely proportional. And that's what this table illustrates. As we increase, if you look from the bottom and go up, if you increase the pressure from 4, 5, 10, 20, 25 atmospheres, increasing pressure, you notice that the volume decreases. 25 to 20 to 10 to 5 to 4. He also noticed that if you multiply these two values together at any one point in that experiment, you get a constant value. Pressure times volume is a constant value. Okay? That's Boyle's law. Pressure times volume is always constant for a given experiment. Now, the one thing that we know now, and they sort of understood then, was that there are 4 factors that can define a gas. Okay? And these are the factors: pressure, temperature, volume, and what we now call moles. That is the amount of gas. Now, those laws came later, the ones involving temperature and moles. But Boyle did understand that when you trap the gas in there, you have that much gas and no more. You can't add, you can't take away. So he knew that was constant. And he also took great pains to maintain a constant temperature during his experiments. And if you do the experiment over a very short period of time, the temperature in the room is going to stay constant. Or, I mean, if you're really, really concerned about temperature variations, you could submerge that whole device in something that maintained temperature, like ice water, right? As long as you've got ice and water together, solid ice, liquid water together, and the ice has stopped melting, so it's at equilibrium, then if you submerge your device in that, you know it's going to be exactly 0 degrees. Well, Boyle didn't have a measurement of temperature in those days. That's why he didn't investigate temperature. But they understood heat, the effect of heat in general terms on gases. All right, so that's Boyle's law. And notice that when you plot them, pressure against volume, you get a curve, this curve. That curve is a special type that you may have been introduced to in geometry. It's called a hyperbola. Remember, a hyperbola is a curve in which neither end, if this is extended indefinitely and extended indefinitely along those axes, never touches the axis. It comes close, but it never touches it. Now, there's a mathematical expression for the hyperbola, right? But when you plot these data together, if P times V is a constant, then you always get a hyperbola when you graph the raw data. Okay? All right. So let me see. I've got something down here that, oh, okay. I mentioned this earlier. The 18th century was referred to as, has often been referred to as the century of gases. That's when most of the gases were discovered and characterized, both qualitatively and quantitatively. But these experiments at the end of the 17th century were absolutely essential to the discoveries that took place in the 18th century. All right, so we have this Boyle's law, and how do you use it, right? Well, if you do this experiment and you don't change any of the conditions, don't change the parameters, then you can calculate what that constant is. And then once you know the constant, then if you know one of the others, you can calculate the missing one. But very often, it's more convenient to not bother with calculating the constant. So how do you do that? Well, like I say, if the experiment is performed under certain conditions and you know the conditions at the start and you know the conditions at the end, then you don't need the constant. And here's why. Under these conditions of pressure and volume, you're equal to that constant. Okay? If you change the conditions of pressure and volume, change the pressure, the volume will change. But it will also be equal to a constant. And those two constants are exactly the same, as long as you have not changed temperature and amount of gas. Under those conditions, the cumulative law of mathematics, if A is equal to B and B is equal to C, then A is equal to C. Yeah. So this is equal to that, and that's equal to this. If these two are equal to one another, then these two have to be equal to each other. Now that's a more useful form of Boyle's law. It's what I call before and after law. If you know these conditions before and you know one of the conditions at the end, then you have an unknown. One unknown, you can always solve for it. Okay, so that's Boyle's law. And these are various ways that you can solve the law. Here's an example. So when you're reading a word problem, you need to decide what type of situation is it. Is it before and after? Are you given conditions of before and after? And maybe one of the parameters is missing, either before or after. It doesn't matter. I mean, if you know how it ends and you want to find out how it started, then you need everything except for one unknown. You can solve for it. So in this case, we want to find the final volume here when 15 liters of gas at 500 millimeters of mercury, 15 liters, 500 millimeters of mercury is allowed for the the pressure to drop to 125 millimeters. So 125 millimeters now is this pressure, and V2 is unknown. That's the one we're solving for right there. Notice that in this equation, you got millimeters of mercury on both sides, which means they will cancel. Then you're left with liters. So under these circumstances, you don't need to change the pressure to atmospheres or anything else. It's a ratio, so you can keep it just the way it is. And just solve the equation for volume like this. Okay? And the final volume turns out to be, you can either rearrange the equation ahead of time, or you can fill in the numbers and then solve for the unknown. It works either way. The only time you would want to solve it like this is when maybe you were going to substitute whatever this is equal to into some other equation. But if you're just going to solve for that value, you can plug the numbers in first and then solve it. But it turns out that that's 60 liters. Right? So if this is right, then as the pressure dropped, the volume increased, right? Pressure dropped to that and increased from that to that. Okay? Other possibilities, right? These are just other types of problems that can be solved, right? So for this one, we want a final pressure. And we actually have different units of volume here, cubic feet. All right. Now, later, after Boyle, scientists were investigating ways to quantify a measurement of heat, temperature. And various suggestions of systems were proposed for measuring the temperature of any substance. We finally settled on three most common. One of those is Celsius, right? Degrees C. Another is Fahrenheit, degrees F. And the third one is just K, Kelvin. Now, we needed a reliable way to measure temperatures, a reproducible way. You needed a scale and the technology to measure that change in heat. Mercury to the rescue again. The Mercury Thermometer was invented to solve that problem. What was discovered was that mercury in a small bore tube, when it was exposed to an increase in temperature, the height of the mercury would increase, which means that the volume of mercury actually was expanding and it had to go someplace. So if you have a narrow bore tube above a bulb of mercury, right, then it would rise to a certain height based on temperature. And if you increase the temperature here, that would expand and it would push up there and give you a new position for the top of the mercury column. Okay, so that was finally perfected. Small bore tubing, all right, that took a little bit more work than the large bore that we were using earlier. And then how to manufacture these things so that they would be robust enough to survive use in a laboratory environment. because you didn't want to use your thermometer with this thin wall down here allowing for heat to transfer. You didn't want your thermometer to just break it at a whim. All right, so that had to be developed. And once the thermometer and the scale to go with it was established, then scientists could use this new technology to investigate the relationship of volume and temperature. Okay, along comes Charles. That's not his first name, that's his last name. Charles is a Frenchman. His last name is Charles. He investigated the relationship of volume and temperature for gases, which took a little bit more work, right? He made this discovery in the middle of the 18th century, right? So it took another, 80 some odd years. Actually, more than that. Probably took almost 90 years before Charles came up with his, after Boyle published his work. But actually, Charles' work was not published in this form. It was picked up by and published by Gay-Lussac, who published some other things as well. But since Charles, Gay-Lussac gave credit to Charles for the work. So after that, it was known as Charles' law, not Gay-Lussac's law. Okay, so what was the investigation? Well, if you compare the volume and temperature of this confined gas, you find that as the temperature increases, the volume increases, right? So it's a direct relationship. We'll talk about temperatures again in a minute. So how did Charles do this? Well, he needed a way to confine the gas in such a way that the pressure and the amount of gas in the confined space was unchanged. It was constant, right? So he had to invent a type of device that would have a constant force on a piston. And here's your confined gas. So once you confine the gas, don't put anything in it, don't take anything away, then you have fixed amount of gas. And then you fix the pressure by using a piston, which you have constant force on top. And then you need to change the temperature. So you need some type of container in which you could alter the temperature and simultaneously measure the temperature, right? So doing that, then you could watch the piston go up and down, and knowing that it was a constant diameter, so a constant volume, then you could relate the height, the movement of the piston to its volume change. Okay, so this is a modern interpretation of that experiment in which we have a temperature measured and a volume measured simultaneously, right? And the points are being plotted over here as we add them to the table. They're plotted on the graph, right? So we notice that as from 0 degrees up to 80 degrees, this trapped gas changes volume, increasing as the temperature increases. So what does that mean? Well, Charles also discovered that this relationship produced a constant value only when you expressed the relationship of volume and temperature in terms of a quotient. Right? Another way of expressing that is volume equals a constant times temperature. Right? But I think it's more instructive to look at it in terms of quotient. Remember, the product was pressure times volume equals a constant. That's inverse relationship. But a quotient of two variables that equals a constant is a direct relationship. And it makes sense. In order for that to be constant, if the volume increases, the temperature has to increase. Right? If temperature decreases and volume increases, then it's not constant anymore. You're changing that value. So in order for that value to remain constant, the ratio of these two together has to be constant. So if volume goes up, temperature has to go up. If volume goes down, temperature has to go down. Okay. So that rule of thumb is the product of two variables equal a constant is an inverse relationship. The quotient of two variables equal a constant is a direct relationship. Now, what they also observed was this temperature scale, right, the Celsius temperature scale, could go negative. In other words, you could go less than 0. Why? Because 0 was established on the Celsius scale at the freezing point of water. And the 100 degrees units is the boiling point of water. Well, they knew, and we know, that there are a number of things that freeze at a much lower temperature. I mean, all they have to do is just add salt to the water and they could get the temperature to drop below that 0 mark. Right? So you could have negative values. So someone got the bright idea. All right, if we plot this volume and temperature against one another and just extend, which is the fancy term is extrapolate the line to the negative, right? And just keep going. So what does that mean? As you decrease the temperature, you're decreasing the volume, which is Charles' law, right? Well, let's carry Charles' law to the absurd. Is there a point where the temperature says that the volume would be 0? The gas would virtually disappear. Well, sure, if you extend that straight line, you reach a temperature on the Celsius scale at which the volume should be 0 for an ideal gas. All right, and that temperature happens to be minus 273.16 degrees Celsius. All right, so they knew that, but somebody else knew that too, and said, well, the logical next step is just make another temperature scale using absolute 0 as your 0 mark. So what's the advantage of that? The advantage is obvious. Lord Kelvin, William Thomson, who, by the way, was born in Belfast, Ireland, but he grew up in England and he did more than just work on the Kelvin scale of temperature. Published this scale in 1848 that's based upon absolute 0 as the 0 mark. So the advantage there is that on the Kelvin scale, there are no negative numbers. Everything is a positive value. It turns out that that is a wonderful advantage to investigating gases. If you don't have to deal with negatives, you don't have to worry about sign changes. And in fact, when you're investigating gases, if you don't use the Kelvin scale, you can run into some really weird anomalies that never solve the problem. Okay, so Kelvin's work, by the way, was inspired by another Frenchman named Sadi Carnot, whose work was in thermodynamics on the heat engine. And a heat engine is like any engine. It takes energy from a high temperature and moves it to a low temperature, and in the process extracts work from it. Okay, that's what every engine in every car and every truck does. It extracts that heat and converts it into mechanical energy. Well, Sadi Carnot's work, which unfortunately was cut short, he died at, I see, how old was he? 35, I think. He died in 1832 during a cholera epidemic in France. And so his research career was cut short. And a lot of his work was buried with him because they were so afraid of cholera. It was so contagious that they thought that all of his papers and everything that he'd been working on was contaminated. So they put it in the grave with him. So it was just a miracle, a stroke of luck, that we had access to some of his work that had already been distributed. Anyway, William Thomson read Carnot's work and worked on some more of his problems in thermodynamics. All right, we'll talk about that in the future. And he saw that there was an advantage, not just to the fact that the Kelvin scale had no negative numbers, was that it lent itself very well to calculations involving thermodynamics. Not just Charles' law, but a broader field lent itself to the study of thermodynamics with absolute zero as the 0 point mark for temperature. Okay, so this is what the Kelvin scale looks like. It starts at 0 right down here and runs to 270, well, 0 on the Celsius scale would be 273.16 on the Kelvin scale. So in order to make the current conversion, Kelvin scale uses exactly the same size degree unit as Celsius. So all you have to do is adjust the 0 point. So if you want to know Kelvin, you just take degree C and add 273 to it. I dropped the 0.16 because for our work, 3 digits is enough. Okay. So Charles made this discovery, and you can use it similarly to the Boyle's law, right? So this before and after scenario. If before your volume is that, your temperature is that, and that's equal to a constant, and then after you're still equal to the same constant, then you can get rid of the middleman. Okay, so there's your before and after. And if you know 3 of those values, you can solve for the 4th unknown. Okay, so there's the trend. Works the same way as in Boyle's law, except with a different arrangement of terms. Oops. It's even worse now than it is face-to-face in the classroom. In the classroom, students just sit there and stare at the board when I make a mistake. Rarely say anything to correct me until I hopefully notice it myself. But when we're Zooming like this, silence is ubiquitous. I rarely hear from students. whether there's a mistake or not. Okay, so these are just different ways to solve the equation, to answer questions. Right? You can arrange the formulas in every different way. Now, the key to using these equations is absolutely essential whenever you're going to do a calculation with temperature in gases. And most examples, right, there are some instances where you can use Celsius temperature in calculations to solve chemical problems. But where gases are concerned, the temperature must always be converted from Celsius to Kelvin. If you don't convert it to Kelvin, then you'll never get the right answer. You cannot leave the temperature in Celsius and do a calculation in using Charles' law or any gas law. So that's the first thing you should do. Change your Celsius to Kelvin. And these are just examples. I'm not going to spend time going through them because you're going to get plenty of practice working the review problems. The question is, am I going to finish on time today? And let's see. I always have to remind myself when this class is over. Where is it? 3:45. So we've got 40 minutes. Okay. So that was, we covered Boyle's law, pressure and volume relationship, Charles' law, volume and temperature relationship. The next one came a little bit later and was proposed by Avogadro, Amadeo Avogadro, who's an Italian. Actually, he postulated it in the first of the 19th century. Okay. But it wasn't widely accepted or used. The power of Avogadro's law was not recognized and used to solve problems until after he was gone. It was the work of a student of his named Cannizzaro, who took Avogadro's law and actually completely revamped his chemistry course. He was a teacher, and he wrote a new text for his chemistry students, and it incorporated Avogadro's law and actually solved a number of problems that were being experienced by chemists in universities and in industry in the middle of the 19th century. In fact, they called together a big conference at Karlsruhe, Germany. It's in Bavaria, southern Germany. And they were called together, these scientists from industry and universities, to try to solve the problem. They were having difficulty understanding how chemical reactions worked, because at that time all they understood was mass, right? They knew that mass relationships were valid. In other words, you have a certain amount of mass of reactants, and then on the product side you have the same mass. They understood that. Conservation of mass had been elucidated by Lavoisier many, many years before. The problem is, when the reaction went wrong, that's all they knew, and they didn't understand why it went wrong. What they didn't know was that reactions are not based on mass. Reactions are based on numbers of atoms of different types of elements and how they arrange themselves. Okay? So it wasn't until Cannizzaro, who was at the meeting, he was like a junior chemist. They didn't pay much attention to him, but he did manage to offer a paper in the public forum, and there was a lot of ho-hum. But he gave the paper copies of it. He had reprints, and he gave the copies out, handed them out to members of Congress as they were leaving, because they were there for several days and they just threw up their hands. They couldn't figure it out. So he said, you need to read this and take it to heart, right? I just skimmed the surface with my presentation in public. Read this paper. And they did. They politely took the paper home with them to their various companies and various universities. And some of them, light bulbs started going on. Say, aha, this is why we don't understand our reactions, because we're looking at them from the wrong direction. Okay, so what is Avogadro's law? If it has such a basic impact on chemistry, what is it? Well, Avogadro himself investigated the relationship of volume of gas as it related to amount of gas, right? So the volume is related to amount in a direct relationship. That quotient again is equal to a constant. So if the volume goes up, the number of moles has to go up. The amount of gas has to go up. Or if the number of moles goes down, all else being equal, the volume has to go down. And what I mean by equal is pressure's constant, temperature's constant. If those two are constant, then this relationship holds. Well, as it turns out, Avogadro didn't express himself very well. He got credit for the law because scientists after him gave him credit. But what Avogadro actually said was that if you have two volumes, those are supposed to be equal. Two equal volumes of gas, and they're at the same temperature, and they're at the same pressure, then they must have exactly the same number of particles that we call moles now. That's what Avogadro said. That being, if that's true, then if you have the same number of particles in each volume, but they have a different mass, then why do they have a different mass? That's because the particles in one have a different mass than the particles in the other. That's how they related masses of gases. Once they knew that this relationship was true, and Cannizzaro developed that for them in that paper, then they could say, all right, if we have, let's just make something up. If we have carbon dioxide in this one, no, let's keep it simpler. Let's say we have two monatomic gases. If we have neon in this one and argon in this one, then we know that the difference between this mass and that mass is because, let's see, neon is 20 and argon is 40, then this volume of gas will weigh approximately twice as much as that one, because each of the atoms weigh twice as much. Now they could relate the mass of the reactants to the actual number of particles. It took some time, but eventually, and in fact, Mendeleev, when he was developing his periodic table, used Cannizzaro's paper and the work that Cannizzaro was developing to inform the way he arranged things in his periodic table. All right, so now we have those three laws. We have Boyle's law, we have Charles' law, and we have Avogadro's law. All right. And you can rearrange Avogadro's law just like, I mean, you can say V1 over N1 equals a constant, and V1 over N2, V2 over N2 equals a constant. So V1 over N1 equals V2 over N2, right? Before and after. And here's an example, right? Maybe we got to look at this one a little closer. Let me see how far I'm getting along here. I know I'm not going to finish today, but we do have a buffer day. We can finish on, what is today? Tuesday? Wednesday. What is today? Wednesday? Yeah, today's Wednesday. All right. Gotta lose track of time. So we've got Monday. We can finish up gases on Monday. And then that following Wednesday, we'll have a review session. So if these are given as initial conditions, if we take, now this is taking it one step further. I mean, we're actually undergoing a chemical reaction here. If you have 35 cubic feet of ammonia at 25 degrees, and it's allowed to decompose, so this ammonia becomes nitrogen and hydrogen gases. Okay? So what does the balanced equation tell us? You're starting off with 2 moles of ammonia, and you're ending up with 1 plus 3, or 4 moles of gas. So this 35 cubic feet of ammonia represents the ratio of 2 moles to 4 moles when it changes. Okay? So how much more volume should it occupy? Right? If you have 4 moles of gas at the end versus 2 moles at the beginning, then we've rearranged it here. This rearrangement here, then you know that the final volume is going to be 70 cubic feet. Okay. Now we have these individual laws. What do you do if actually more than one thing is being changed, right, in the process? Well, there's a combined gas law. So if we say that pressure times volume equals a constant, and volume divided by temperature equals a constant, and volume divided by moles equals a constant. These are different constants, by the way, right? Not to imply that they're the same. But if those are true, then what's the relationship we can combine those laws, right? And this is what they look like. If we combine these two, we get pressure times volume divided by temperature is equal to a new constant. Or if we were to combine these two laws, we would get
volume divided by temperature times moles is a different constant. But if we combine them all, we will get pressure times volume divided by temperature times moles equals a new constant. 4.
So that's the combined gas law. And to prove it to yourself that it works, you just say, all right, let's use the before and after version. I think it shows it a little better.
So if we use P1 V1 over,
okay, that's sliding off here. There we go.
P1 V1 over T1 N1 equals P2 V2 over T2 N2.
That would be a combined gas law before and after. What if we held temperature and moles constant? Right, these two are constant. If they're the same on both sides, they cancel. So now you have Boyle's law. Or if we hold pressure and moles constant on both sides, you get Charles' law. And if you hold pressure and temperature constant on both sides, you get Avogadro's law. Okay, so it is a valid expression. Now with this one, you could have this pressure, this volume, this temperature, and that number of moles. And on this side, you could have this pressure change and a different temperature and a different number of moles, and you could calculate the volume afterwards. Okay, so it's a much more powerful equation because multiple variables can be changing. As long as you only have one unknown left over, then you can solve for it. And that's what this slide does. Shows those adding. Now, I've got just a few minutes and I'm going to cover one more law. And actually, it's a type of combined law. It's called the ideal gas law, or the ideal gas equation. Suppose you are in a situation where you only know the state right now. You don't know a before and after. You don't know a change. You just know what it is right now. Are you stuck? Well, with the laws that we've expressed up to this point, yeah, you're stuck. But if this is equal to a constant, which it should be, then if we establish the units of measure here, 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 and here, we should be able to calculate what that constant is with those units of measure. Right. So what we're going to say is try to keep things standard. So at 1 atmosphere pressure, and 0 degrees Celsius, which is what in Kelvin? 273, 0.16 K for temperature. And 1 mole of gas what volume does that occupy? Well, you have to measure that one. The volume that it occupies is actually 22.4 liters. Right. So under those conditions of atmospheres, liters, K for temperature, and moles, this value is 0.00826, I think. Let me do the calculation to be sure. I'm working from memory.
So let's say 1 times 22.4 and 273.16 divided into that, 1 divided into that. 08206. Yeah, I'm a little off. I think these values are a little off. But this is the value we're going to use. This is the constant under those conditions with liters, atmospheres, K, and 1 mole of gas. So that value now has units of liter, atmospheres, per mole K. Right? Now, that can be substituted here for this. And in fact, we changed that K to a new symbol. We make it R. Okay? This is the ideal gas equation. Although we usually solve it, we rearrange it so that it looks like this. PV over here, and we take those two and put them over there. N, R, T. That's the ideal gas equation. And when you're using this one, you have to be extremely careful to use the right units of measure. And the units of measure are based upon what's in this constant value. Your volume has to be liters, your pressure has to be atmospheres, the amount has to be moles, and the temperature has to be K. If you do that, then you can say, what is my state? What is the situation right now? And if one of the terms is missing, solve for it. Say if you know this one, and that one's a constant, you can solve for the temperature under those conditions at that particular point. Right? So we have two types of problems in the gases. One is before and after, in which case you could use the combined law that we showed earlier. And the one is the state situation. What is it right now? And when you read a problem, that's what you're looking for. Is it giving you information for what's happening right this instant? Solve the problem? Or is it changing from this one to that one? In which case, you can use the combined gas law or one of the simpler laws. Okay, so let's see. I think this is a convenient place to stop. I didn't show you all the slide, of course. Oh, I didn't even show you that. Okay. We'll come back and pick it up here with the ideal gas. What is an ideal gas?